All right, this is the video lecture for Algebra 2 class on July 15th. All right, so today what we are going to cover is we're going to continue working in Unit 3 here, but obviously we're going to go to 3.4, 3.5, and 3.6 here. Okay, so to give you a quick overview of what that's going to look like. All right, we have one quiz and one extra credit journal for 3.4. In 3.5, we just have the one quiz, and in 3.6, we just have the one quiz. All right, so hopefully today's a little bit easier. That's kind of my hope, is that you just have 3 units, 3 quizzes, and if you'd like to, you have that extra credit opportunity always, right? Or anytime it's available, you have that. All right, so if we look here, all right, we introduced ourselves to exponential functions, right? Now we're going to talk about what do the graphs of those look like here, all right, and how do we perform operations to change the look of those exponential functions, all right? So if we get into it here. All right, we learned some of the terminology here, but again, to remind us, all right, in exponential functions here, right, we've got our b value raised to the power of x, and we even talked about having an a value out in front, but we'll introduce that a little bit later here. All right, but again, b is our base, and it is raised to the exponent here of our value x. All right, so that's what we're looking at with this original expression here. All right, so when we look at this, all right, we have 4 different graphs down here. All right, again, b is not negative for any of them, right? And b does not equal 1. So that's what this is saying. B is greater than 0, so it's not negative, and it also doesn't equal the value of 1, right? Because like we said, anything raised to the power of 1 is just going to be 1, which, you know, that's no fun to talk about. All right, so if we look here, okay, they're all raised to the same exponent of x. All right, they're all raised to the same exponent of x. All right, but then question 2 is saying, what is the base of the exponent when the graph increases to the right or when it decreases to the right? That's what we're looking for here. So if I look at my 2 values less than 1, all right, I've got my 0.5 and my 0.2. Okay, so obviously those are decreasing as we go to the right. And if I have values greater than 1, 2, and 3, you're going to notice that those are increasing. All right, those are increasing. All right, so again, if we have our b value less than 1, right, it's going to be that decreasing or that decay function. And if we have it greater than 1, it's going to be increasing, right, in our increasing function. All right, and that's what this is saying here. If b is greater than 1, graph increases. If it's between 0 and 1, then the graph decreases. All right. And another thing to note here, again, the base can never be a negative number. All right, the base can never be a negative number because it is undefined. All right, because it would make it undefined for a lot of values here. All right, so we don't want to do that here, okay? And here is saying we can click and drag the red dot to see what happens when our b value is changed. So right now our b value is 2. If I make it 4, obviously it increases faster. All right, if I make my b value between 0 and 1, okay, obviously we have that decay function. All right, and again, we don't go any farther than that, right? We can't go over here in this negative region because, again, that's where our graph becomes undefined in locations. All right, so we're going to deal with, obviously, positive values for our base. All right. But moving forward here, okay, we want to make sure we can identify a couple major points here in our exponential functions. All right, so when we look at our graph here, okay, in general terms, if we have our b to the x, all right, it will cross or our y-axis or our y-intercept at 0, 1. All right, it will cross at 0, 1, and it will always cross at 0, 1, and we'll talk about that in a second. All right, and when we look at, again, just b to the x, it will always have the point 1b, where b is the base of the expression. All right, and if we think about this here, right, this is saying our x value is 0 or our x value is 1. So we have it raised to the exponent of that x value. All right, so think about it here. For here, anything raised to the power of 0 is going to give you an output of 1, right? So hopefully this is making sense here logically, right? And if you don't believe me, plug it into your calculator. I promise you will get out the value of 1. But any number, 14, 105, 62, to the power of 0 is going to give you an output of 1 here, all right? And then, similarly, all right, if I raise it to the power of 1, that's just the base value by itself, right? So these 2 points here should be kind of obvious when you sit down and really think about it here in terms of real numbers, all right? And what that's going to do here is it's going to change our graph. So if we look here at 2x, right, I will always have that 0.01, okay? I will always have that 0.01, but when I'm at the value of 1, it's going to be at 2. And lo and behold, yep, it is. All right, if I bring this out to 4 here, all right, it's going to be a point at 1, 4, or 3.99 in this case, since I didn't make it all the way to 4. All right. Even when I go between 0 and 1 here, look, hopefully you're noticing that intersection point does not change. That intersection point is still going to be at 0, 1. All right. And if I go to half, right? If I go to 0.5 raised to the power of x, all right? Still, when I am at 1, when my x value is 1, I'm going to be at my b value. And again, if you trace it across, it's at that half increment, right? So this is, again, the point at 1 and 0.5, all right? All right, and again, we already explained this, but again, plug in real values if you don't believe me, all right? So, again, looking at these different functions, okay? So since we know that always looking at the x value of 1, okay, it's going to have that 0.1b, where b is our base. We can then start to look at some of these graphs here and already pick up as to what the equation is probably going to be. So if you look here, okay, this is at 0, 1, awesome, we've got that intersection. All right, at 1, it goes up to the value of 4 here. So my base value is going to be 4, and lo and behold, I have a value of 4x. All right, with this one here, it's a little bit harder to see, but it goes all the way up to this value of 9 here, right? And if, again, this went up, you would be able to see that it's exactly on that mark, okay? Same thing down here, all right? Even though that these are decreasing, right, that should immediately send off some kind of signal in your head like, okay, it's got to be a value between 0 and 1, all right? And then you look on your graph and you see where that point at 1 is, right? This looks like it's at 1, and when it's at 1, it's at about a half, right? So I would guess a half, and lo and behold, I'm right there, okay? And if I look at this value here, maybe that's like a third, or maybe a fourth, all right? Perfect, all right, there we go. It's at 1/4, all right? And again, hopefully we're not doing too many of these kinds of things here, but always you can just draw a straight line, trace it up, right? Trace those values up there, okay? So again, we've identified 2 really good common features here that are going to help us. Another one here is this thing called the horizontal asymptote, right? So we introduced ourselves to vertical asymptotes, where again, it is a line that the graph does not cross. It gets really, really close to touching, but it never actually touches. All right, so we have the same thing here with our horizontal asymptote. All right. And if we look here, right, this graph gets really, really, really close to what looks like our x-axis, right? It gets really, really close to our x-axis, but it doesn't touch, right? Believe me, right? If I move this, I know it gets really, really difficult to see down there, but if we were to zoom in, you would see that it gets really close, but it's not going to touch, because think about it. Okay, how could I get a value equal to 0? How can I get a value raised to the exponent equal to 0? All right, same thing, even if I go between 0 and 1, look, you're going to notice I'm still going to approach 0, right? So that is a horizontal asymptote where, again, it gets really, really close, but it never touches it, okay? Now, we're going to deal with our domain and range. Again, domain being all the possible x values and range being all the possible y values, okay? So if we look at this, all right, our domain, our x values, well, we can go all the way to the left, all the way to right, forever and ever and ever, right? So our domain is going to be the set of all real numbers, okay? It's going to be all real numbers, all right? Because we can plug anything into x and get a value out, right? Any real number we can plug into x. All right, but what's going to be different here is our range. Okay, our range, think about it. What values can y equal? Well, it can definitely keep going up and up and up, but we just said that it can't equal 0 down here, or it gets really, really close to our 0 point. So our range here is the set of all positive numbers, all right? It's the set of all positive numbers, or we would say greater than 0, right? We could say greater than 0 also. All right. So then looking here, if we now go to a little bit more involved or slightly more complicated version of our exponential function, right? We add in that a value out in front. Okay, we add in that constant that we can multiply by, right? So what happens there, it still has the increasing or decreasing nature based on our b value, all right? And it's still going to have the same shape, still going to have the same range, domain, and horizontal asymptote, all right? But the difference here, the difference being, all right, our y-intercept and that other point that was originally at 1b, right? It was at 1b. So if we look here, these values instead, our y-intercept instead of being at 0, 1 is going to be at 0a. All right, it's going to be at 0a. And the other point's going to be at 1 and a times by b, right? Originally this was just 1b, now this is 1a times b, all right? And again, if we look here, we've got the value of 2, so at normal, right, our normal graph here would be at 0, 1, okay? It would be at 0, 1, all right? But now it's at 0a, and our a value for this green graph here is 3, so that's going to be at 0, 3. All right. When we look at our x equal y points, when we look at our x equals 1 points, our original graph here is at 1, 2, right? It's at 1, 2. However, our new graph, our green graph here, has to be at 1, comma, a times by b. So a is 3, our b value is 2, so this should be at 1, 6. Right? And lo and behold, it is. Right? And that trend is going to hold true for the different values. Okay, it's going to hold true for the different values. Negative, or not negative, I'm sorry. The values that are less than 1 and the values that are greater than 1. Okay, it's going to hold true for both of those. All right, and again, believe me or not, right? You can always plug them in and check for yourself here too. Okay, but that's the major difference here when we start adding a constant value out in front, is we change those 2 points. All right. Then, of course, once we've identified some of the base characteristics here, we need to go into our translations, right? How do we translate those graphs? All right, so the first way we can do that is through vertical translations, right? Moving things up and down, all right? And lo and behold, you're going to find out it is exactly similar to what we've been doing with our other graphs. So to shift 5 units up or shift 3 units down, we, again, just move up 5 or move down 3, all right? And what we do is we just add it on to the end. So we've got our 2x and 2x. When we shift 5 up, we go plus 5. We shift 3 down, we go minus 3. All right? When we look at our horizontal translations, moving left and right, okay? Again, it's going to be the same thing, but now we have to subtract or add to our x values. So again, we shift right, we shift left. The graph shape doesn't change, right? It just changes its location. So when we do that, it's now 2 to the power of x minus 1. Again, when we subtract from our x value, we move to the right, whereas we add, we move to the left. Okay, so we move 6 units to the left, so this is going to be 2 to the power of x plus 6. 2 to the power of x plus 6. okay? And again, you can always double check a couple easy points there and verify that that is true, right? And some of the values I love to put in for x are obviously going to be 0 and 1, right? Those are the values I love to put in. What happens when x is 0? What happens when x is 1? All right, trying those points out. Okay, now that we've talked about moving left, right, up, down, we're going to talk about stretching and compressing, okay? So again, to vertically stretch something, we're going to multiply by a number greater than 1. To compress it, we're going to multiply by a number between 0 and 1. All right, so again, if we look at our original function of 2x, okay, we vertically stretched it, so we pulled it away from our x-axis, right? We stretched it, we pulled it away from our x-axis, all right, by 4 units. So we multiplied it by a value of 4. If we wanted to compress it, right, we're getting closer to our x-axis, all right, we would multiply by a number less than 1, and in this case, we did 1/3. All right, we did 1/3 there. Okay. And looking at our domain and ranges here, okay, I know I skipped over on the last ones, but you can always go back and look. All right, our domain still stays all real numbers for both of them. All right, and our range for this one is unchanged. Okay, our range for this one is unchanged. All right. Obviously, with some of the other ones, you're going to have a little bit more drastic change, but again, it's always just going through the same process here. Domain being our x values, our range being our y values. Okay. Now, if we want to look at flipping, okay, if we want to look at flipping, all right, if we multiply by a negative number, it flips it across the y-axis, all right, it flips across the y-axis, all right, and we're talking here, we're talking here about horizontal stretching and compressing instead of vertically now, all right, so let me go back here for 1 second to clear that up. All right, so if we want to horizontally stretch or compress, we can do that, and we'll talk about that in a second, but we can also multiply our input value by a negative number, and when we're talking about horizontal stretching and compressing, if we make that a negative value, it also flips it across the y-axis, right? It flips it across the y-axis. But when we're talking about horizontal stretching now instead of vertically, okay, if we wanted to horizontally stretch by 1/5 of a unit, right, by 1/5 of a unit, what you're going to notice here once we get there, all right, is we now multiply our x value by 1/5. All right, we multiply our x value by 1/5. All right, same thing. If we want to horizontally compress by 8 units, right, we're going to multiply our x exponent by 8. So we're going to have 8x as our exponent there. All right, and again, the domain and range are not going to change for those values. Okay, they're not going to change for those values because we're just stretching and compressing what values we already have pre-existing. All right, and obviously we can put it all together here now. We can definitely put it here together. All right, so again, refresher, I know we know how to do most of these, but I just want to look at this one. If we vertically stretch by 6 units and we flip over the y-axis, all right, so what we would do is we would vertically stretch up by 6 units, and then if we reflect or flip across our y-axis, right, we flip across the y-axis here, all right. And as a reminder, if we want to flip across our y-axis, like we just said, you have to multiply by a negative exponent, right? So we just wanted to flip across the y-axis, right? We didn't want to do any horizontal stretches or compressions. So since we just wanted to flip there, we just multiplied by a -1 out front, okay? If this was, we wanted to flip across the x-axis here, right? Instead of being a +6 here, this would be a -6. All right, so that's again the main difference here, similar to what we've already done. If we want to flip across the x-axis, you multiply the x value by a negative value versus multiplying the entire function by a negative value. All right. Okay, so then moving forward back to the penny problem here, okay, again, we were able to figure out that if we doubled a penny every day, it would end, for a month, it would end up being about $10 million by the end of the month. And again, the reason being because it has this exponential growth that happens really, really quickly. All right. And looking here, all right, this is showing you the same thing. Day 1, day 2, day 3, day 5, right? Same thing graphically here. Or your money goes up and up very rapidly when we do raising to the exponents, right? It goes up very rapidly. Okay. So now if we go here and we move a little bit forward, all right, I want to just take a second to really dissect. If you have a equation that looks like this, there are multiple things you should notice here and questions that you should ask. So this is a good one to really walk through here. All right, so first off, is this function a reflection of a parent function? If so, what kind? If so, what kind? And look, we have a negative value. It's not to the x directly. It's out in front. So we do know it's a reflection because we've got a negative value. And since it's not to the exponent itself here, we know it's a reflection across our x-axis. All right, since the parent function was multiplied by a negative number, right, and it reflects across the x-axis there. All right. Was the parent function translated, right? Up, down, left, right. And the answer to that is going to be yes, right? Look, we've got a +4 there. So it was translated up. It was translated up by 4. All right. If we were going to move left or right, it would have to be up here in the exponent. So it would be raised to the power of x plus or minus, right? Okay, and then the last question, was the parent function vertically stretched or compressed here to create the function? And the answer is, yeah, look, I've got it multiplied by 3 factors. So you've got to remember, what does that mean? All right, and since I am multiplying by a number greater than 1, I am stretching it. All right, I am stretching it. And obviously, we already addressed the negative sign there, so we don't have to re-deal with that. All right, but that's how we can dissect this entire function here. We can dissect it piece by piece, asking basically those 3 questions, right? Is it a reflection? Was there a translation? And is there a stretch or compression? Right? That's pretty much the 3 main questions you've got there. All right, and if we looked at what those individual pieces looked like here, multiplying by a -3, right, we know we flip across the x-axis and we have that stretch, okay? If we go up by 4 only, we know we move our function up 4, and then when we add them both together, right, they're flipped and then moved up, all right, or sorry, flipped and stretched, right, then we move it up by 4. So that's how we get to our final graph here from our parent function of 4 to the power of x. All right, looking at the graph of an exponential function, it is always a curve. Okay, it is always a curve here. All right, and what characteristics does the graph have? Right, it's always a curve. It's going to have that point at 0a and that point at 1 comma a times b. Right, now those are going to be your main characteristics there. And then obviously, if b is greater than 1, it's going to increase going to the right, and if it's between 1 and 0, it's going to decrease going to the right. Being that decay type shape. All right, so those are your main characteristics here with exponential functions. All right. And I'm going to let you guys do these problems on your own because, again, it is really, really important for you to at least try these problems to get some instant feedback here. But, again, dissecting and making sure that you're really asking the questions, what's going on with this graph here, right? Is there any modifications to the parent graph, and then if so or if not, how does that affect our intercept, our key points, and how does that affect our domain and our range here? All right, so if I look at this first one with you, right, I'll leave you 2, okay, first off here, it's 6x. So we know that it is not translated, it is not stretched, it is nothing. It is just a base function on its own here. All right, so since this b value is greater than 1, we definitely know that it is increasing, right? It's going to be increasing. So immediately we mark off choice C. That is not possible. All right, with this base function here, remember we said our domain, our x values, okay, our x values, this is saying the domain is x is greater than 0, and that's incorrect. That's actually incorrect here, right? We said our domain is all real numbers. All right, our domain is all real numbers. So immediately that marks off choice B here. So now we're just dealing with choice A versus choice D here in terms of our options, right? Because they both have the values of A so far. All right, and we said the intercept, the y-intercept, and this seems to be the deciding point here between D and C. All right, the y-intercept, since it doesn't have an A value, okay, our y-intercept is going to be at this point 0, 1. Right, it's going to be at this point 0, 1. All right, it's going to be at this point 0, 1, or 0, comma 1. All right, then just to verify per always, right, it says and E. All right, so our range is y is greater than 0, right? And we did say that, right? Our y values have to be positive since there's no translation to this function. All right, and then obviously f is not true because it says it is decreasing, which is obviously the opposite of a, which we know was true. Okay, so now, again, there's two more problems that you get to work yourself through here following that exact same process. Figure out if there's any modifications to the parent. If so, or if not, what does that mean in terms of the rest of these characteristics here? Okay, same thing, I'll let you guys click and try these ones, but the main difference I immediately notice, okay, is some of these are increasing and some of these are decreasing. All right, so that should be one of the key things that you can look for. Is it increasing or is it decreasing? All right, so that should be the first thing you look for. If it's decreasing, right, if it's decreasing like this guy or this guy, right, if it's decreasing, you need to notice then that means that the base value is going to be less than 1, right? So that cuts your options in half already. All right, so you're looking for if it's increasing, decreasing, and then the next thing you should look for is those key points. At 0, is it going to be 0, comma 1, or is it 0, comma your A value, right? That's going to be another deciding factor there, all right, between some of these graphs. All right, so those are my two helpful hints for helping you get through that. All right, now that we understand this a little better, we can look at this rabbit family problem. Okay, so if we look at a real world example of exponential functions, okay, it shows that this particular rabbit family grows at this rate here, where P of X is the population of the rabbit family in any generation of X. Okay, so the first generation, X is equal to 1, and the population is 2, right? Because 1 minus 1 gives us 0, okay? 3 raised to the 0 power gives us 1. 1 times 2 gives us 2, all right? Based on this function, in what generation will the population have more than 50 rabbits? All right, that's the question we're looking for. So we need a value of P greater than 50, okay? It says, you are given P of X and you must find X. What tells you that? Right here. In what generation will the population have more than 50 rabbits? Okay, so P of X is going to be 50 here. And we've got to solve for our X value. Okay, we've got to solve for our X value. Okay, so then if we were to graph this function, we could look at a table of values. We could look at our graph here. All right, you could plug in some values, but since we're dealing with a real world problem, okay, since we're dealing with a real world problem and it's talking about X being different generations, right, we are only going to have whole numbers, right? You're not going to have 1.5 of a generation, all right? So we're only dealing with whole numbers, which is why this table here in this graph is pointing out the specific values at 1, 2, 3, and 4. That's saying first, second, third, and fourth generation here, all right? And obviously, both of these are going to tell you the exact same answer, all right? It's going to tell you that at the fourth generation, we will have at least 50 rabbits, right? At least 50 rabbits will be had in this fourth generation, right? Obviously, we have 54, okay? So then that would mean, again, that's how we solve our answer, okay? That would be how we solve our answer, all right? And as it's pointing out here, looking at the table or looking at the graph here, okay, obviously is a pretty simple way of figuring out how to do this, but in the next unit, we're going to talk about how to actually mathematically undo it without plugging in values here, and that's going to be called our logarithmic function, right? And we'll deal with that in the next unit here, okay? But these 4 questions here to further check your understanding. Okay, obviously knowing the key characteristics of our base function where it's b to the power of x is going to be really beneficial for this first problem here. All right, then knowing what happens when we multiply by a constant, right? That's what this one's asking you. Okay, same thing with this guy here, knowing beyond just the base characteristics, what does our y-intercept look like? What does that other key point look like if we have our base function of 1/4 here? All right, and then being able to identify those key characteristics graphically and matching it up to a possible graph here. All right, so those are my helpful hints for you solving those problems here. Okay, if we take a quick look at our study sheet, all right, All right, in general, exponential functions, the base value has to be a positive real number. Okay, the base has to be a positive real number. All right, the base cannot be negative, imaginary, 0, or 1. Okay, that's going to be super important here. All right, again, identifying what happens when b, our base value, is greater than 0 or between 0 and 1. That's increasing versus decreasing. All right. Looking at both our b of x function and our a times b of x function, there's going to be things that are similar, obviously, okay? And then the main differences here being what happens at our y-intercept and the other known point, okay? The difference being instead of being at 0, 1 or 1b, it goes to 0a and 1 comma a times b. All right, so again, that point gets modified by the presence of that a value or that a constant out in front. All right, they both have the same horizontal asymptote and they both have the same domain and range. All right, and this table here is going to be really beneficial for helping you solve a lot of problems. Okay, it's going to be really beneficial for helping you solve a lot of those problems. All right, if we look quickly at our practice problems, per usual, I'm going to suggest that you do at least a couple of these here. All right. And again, my suggestion would be pick one where the base value is less than 0. Pick one where the base value is greater than 0. Pick one where it's just b to the power of x. Pick one where it's a times b to the power of x. Right? Really looking at that stuff here. Okay? And then knowing, obviously, how to translate the function. So if there's values, are we adding, are we subtracting? What does that mean? All right, and don't let this confuse you. Don't let it confuse you. You've got this 4 out in front. It's 4 plus 2x, right? Okay, you can move that behind if that's going to really bother you, but remember, we're just adding 4. We're adding 4 here, all right? But then looking at, I've got 8 minus 3x. Well, can we really have a negative base value? We said no. So what does that mean? What is that going to look like, right? Taking a minute at least to look at the answers as to how we solve that one. All right. And then for 7 through 10 here, the last problems are, of course, again, identifying the major characteristics. What is the base value? Is it greater than or less than 1? All right. Is it, what's the point at our x equals 0? What's the point at x equals 1, right? And that's going to solve a lot of questions for you. Okay, that's going to help you solve a lot of questions. All right. And then, like I said earlier, okay, we've got this one mandatory quiz, and this journal is extra credit if you'd like the opportunity to get some points here, right? Again, partial credit is accepted. Okay, so then moving on, as promised, we're moving towards logarithmic functions here, okay? Logarithmic functions. So we kind of gave a prequel, okay, that's going to be the inverse of our exponential function. All right, so taking a look at what logarithmic functions are in general, okay, they are going to give us, again, the ability to undo our exponential function if it's in this form, b to the power of x, all right? And remembering the definition of our inverse is it undoes the work of a function. So if I have a raised to my exponent here, I can use my logarithmic function to undo this. All right, I can look and undo this here. Okay, and if we look at this inverse tool here, okay, remember, in order to see the inverse, we can reflect our graph across this line y equals x, and that would give us our inverse. All right, it would give us our inverse here. Okay, so sorry. Okay, so if we look at our original function here in blue, it is g of x here, okay? And you can see this red line stands for our horizontal line test, because obviously if we have a one-to-one function, right, if we have a one-to-one function in our regular, we will also have a function in our inverse, right, in our inverse. So if we look here and we flip it across this line, y equals x, okay, we can notice that we can still have our inverse being a function here, okay? Our inverse being a function. And I know it gets really difficult, but again, believe me, if I zoomed in really close, you would see that this is still moving ever so slightly closer and closer and closer to this y equals 0 line, or in our original function, this x equals 0 line, okay? So again, like I just told you, okay, does the graph of the inverse pass the vertical line test? When we flipped it across, it does. All right, it does. So that means the inverse of an exponential is also a function. All right, and if I restart this here, okay, like I said, if we go down like here, okay, let's look at x equals, or I'm sorry, if we look around this, y equals negative 10 here. All right, so if I zoom in really, really close, you can see that clearly it's getting ever so slightly closer. All right, ever so slightly closer. All right, so we're able to notice that, again, it is going to be this function here. All right, and I can still pull this red line even when I'm really, really close. Okay, you're going to notice it's only crossing at one point. All right, it's only going to cross at one point. All right, so the inverse of our exponential function is also a function. So this logarithmic function is also a function, okay? And obviously, like we said, I've already been telling you this, the name of it is this logarithmic function here, okay? And the reason we call it a logarithmic function, or I guess the way that you could know that it's a logarithmic function, is it literally says this word log, L-O-G. Okay, L-O-G stands for logarithm, right? And how we write them is this we say log base b of y, right? Log base b of y. All right, and that's how this is written here, right? And again, remember, if we have f of x, right, this is like saying y, okay? So f of x is equal to bx, which is equal to our y value, right? So when we take the inverse, right, we can flip our x and our y values and then still solve. All right, so we have f of negative 1 of y is equal to log base b of y, right? Log base b of y. All right, and again, as you saw here, it's going to have this shape. So if we look at our graphs on the same, both of our functions on the same graph here, okay, obviously our red one is our exponential function that we've been working a lot with, and now this blue one that we just got introduced to is our inverse of that exponential function, which we now know is this logarithmic function, right? It's got its own special name, this logarithmic function. Okay, so hopefully what you notice here is if I'm at x equals 2 in my original expression, all right, that is written as 2 to the power of x, right? It's written as 2 to the power of x. Okay, and when we are in our inverse function, we now take our base value, b, and that's again now our log base. Okay, so this is 2 to the power of x, right? Or our base value here is 2, right? And when we flip it and take the inverse, this now becomes our base value. So we have log base 2, all right? If I have 4 here, right, 4 to the x, it still is log base 4. Log base 4 there. Okay. Now, moving forward here, okay, how does this actually work mathematically? How does this actually work mathematically? All right, so if you can start with the log, you can start with the base, whatever you want here, all right, but using the same letters for both of them, all right, if I have b to the power of c equals a, b to the power of c equals a. If I'm trying to undo this function here, I can write it as log base b of a. is equal to c. Right? So basically, what my log is trying to solve here is it's answering the question. So if I have b to the power of c equals a, right? The log base b of a is basically asking you here, if I have an output value of a, right? What is my exponent that's going to make this base value equal to my a? What is the base value that's going to make what is the exponent that's going to make my base value equal to a? All right, so if I look here at log of 10 equals 2. All right, log of 10 equals 2. The reasoning behind that is saying, again, 10 raised to the power of what is going to give me 100? Or 10 raised to the power of 2 will give me this value of 100. All right. If I look at this one again, log base 3 of 81 equals 4. Also like saying 3 to the power of 4 equals 81. 3 to the power of 4 equals 81. Now, if we get smaller numbers, this is where it might get a little bit trickier. All right, so log base 9 of 3, all right, equals 1/2. So this is like saying, again, 9 raised to the what exponent will give me a value of 3? Well, as we found out, again, 1/2 is like saying square root. So this is like saying the square root of 9 equals 3, or 9 raised to the 1/2 power equals 3. All right. And then the final example here, log base 2 of 8 equals 3, or like saying 2 to the power of what will give me a value of 8, and the answer is 3, because 2 raised to the 3rd power gives me 8. All right. And I know this is a new way of thinking here, so take a second and really digest what this means here. But again, it's asking the question, okay, the b value raised to the power of what will give me this a? Right? That's what we're trying to solve for when we look at logarithms. Okay. Now, we just looked at a lot of different base values, right? We had a base 4, a base 9, a base 2. Okay, but there are 2 specific bases here that we're going to talk about when we're dealing with logarithms. Okay, the first one is if we have a base 10 value. So log base 10, log base 10. Okay, this is what's called our common logarithm. Okay, this is what's called our common logarithm. It's the one you're most likely going to see. All right, and normally, when we're dealing with base 10, you probably will just see it as log, like by itself, right? So again, instead of writing log base 10 of x, okay, with this common logarithm, again, base 10, we just write it as log of x. All right, we just write it as log of x. And on your graphing calculator, you actually have a log button, okay? It is the 4th button up on your graphing calculator. It's right there, that log button. Okay, that is log base 10. Okay, that is log base 10. That assumes base 10. All right. Now, the other common or special base is called the natural logarithm. Okay, and that is where we have base e. Right, so this would be log base e of x. All right, log base e of x. All right, and how we say that is that one is called our natural logarithm. Okay, that's called our natural logarithm. Okay, and what that one is it's written as ln of x. ln of x. All right, and that is a lowercase l. Okay, that's a lowercase l for natural logarithm. All right, and again, we have a button for that. That's right here. It's ln. Okay, and yes, I know it's a little bit confusing. It's written in capitals here just to make it very clear as to what the letters are. But when we write them as math equations, they're lowercase. All right, but we have that ln or that natural logarithm button. All right, we have that natural logarithm button. Okay, and again, looking back and forth at how to solve these. All right, so this is saying log base 10 of x, or our common log, right? So log of 10. Log base 10 of x equals y, or like saying 10 to the power of y equals x, right? 10 to the power of y equals x. All right, same thing here. except for instead of having it be a base 10, it's this base e value. So again, when I'm going back and forth between my natural log, okay, if I have ln of x equals y, right, this is like undoing e to the power of y equals x. Right, e to the power of y equals x. Right, so that's our difference between our common log, again, base 10, and our natural log being this base e. All right. So a logarithm function is the inverse of an exponential function. All right, that's going to be really beneficial for us. All right, and then taking a look back, if you need, at what's the relationship between log and exponential, right? That's inverse. How do we go back and forth? How do we evaluate, right? How do I approach looking at those problems? All right, and then we just went over common log being base 10, natural log being base e. Okay, I'm going to leave these for you to try because, again, I think they are super beneficial for understanding what they are stating. Okay, understanding what they are stating here. All right, but I do want to point something out. Again, ln, this is our natural log. And then if you just see log with no base, right, it says log of 7, you can assume this is base 10 here. All right, this is base 10. Okay, this is base 10. All right, so please try those out. I think they're going to be super beneficial for you. Okay, so then again, you can concept check these with some multiple choice here. Again, looking back at your study sheet, which will have the conversion back and forth, I think will be really beneficial for you. But understanding that, again, if I'm trying to solve for C here, that's an exponential equation. So to undo that, I'm going to have to use its inverse, which is a log function. All right, so the answer for this one, okay, the answer for this one is going to be log base 7, all right, because that's my base value, so log base 7, so immediately we're dealing with A or D, log base 7, all right, of 49. Okay, so again, log base 7 of 49 equals C, because this is like saying 7 to the power of what will give me 49. So my answer is going to be D there. Okay. I'll let you try this one, but again, this is using our log base E. So our log base E is natural log, right? So our log base E is going to have this natural log or ln function there. Okay, then I'm doing it. If I have ln here, like I just told you, it's a base value of E. So your answer better be E to the power of something. E to the power of something. All right. Same thing here. This is log base 10 of 300. Since you don't see a base value there, you assume it is base 10. All right, so it's a base value of 10 there. Okay, so then moving into our study sheet here. All right, pretty quick one for this study sheet. All right, understanding our exponential function and its inverse, the logarithmic function. Okay, with our exponential function, our input is x versus our logarithmic, right? We know we flip those, so that's our y. All right, they both have the same base of b, which should be super helpful for you. They both have the same base value, which is b there. All right, and they ask a little bit different questions than I do, but the question they said here is, what do you multiply when you get b multiplied itself x times, versus how many times do you need to multiply b by itself to get y? Right, so that's the questions they ask to help answer it. All right. And then obviously looking at if this is our original function, our inverse is reflected across this line y equals x. All right, it's reflected across y equals x. All right, and then converting between the equivalence forms. All right, knowing how to go back and forth from either of these forms is going to be super beneficial, especially again with our common log of base 10 and our natural log of base e. All right, in the real world, when you move beyond just this math class, okay, you're more likely going to see the common log or natural log based functions. All right, so really knowing how to go back and forth with these guys. All right, moving to our checkup here. All right, if we look at our checkup, obviously we know this is going to be a lot of questions here converting from log to exponential form. All right, log to exponential form, and this has a lot of varied bases here. So again, if it's not existent as a base and it's still a log function, it's a base 10. All right, and that's going to be important here. Okay, so if you've got a base 10, that's going to be your common log. If you've got a base E, again, that's your natural log. So really paying attention to those special cases there. All right, and then that pretty much finishes up our introduction here to logarithmic functions for 3.5. So you have one quiz on that, right? So far we've covered 2 units, we've got 2 quizzes, and 1 extra credit opportunity. All right. Now taking a little bit more in-depth look at what the graph of our logarithmic functions look like here for 3.6. All right, we're going to take an in-depth look at what those graphs look like. All right, and what they're saying here to actually type them in on your calculators, right? You're going to use, if you're using the natural log, you'll use ln, and if you're using a log base 10, you're going to hit the log function there. Okay, and I've never looked at that calculator. It's kind of funny. All right, same thing here. The log base 10 is right there, and natural log, or ln, or I'm sorry, log base E, or our natural log, is right there with that ln button. All right, and what you should hopefully notice here is that if we have a log base 2, we don't have a button for that. And we'll talk more about what do you do when you get to that later on in the unit here. All right, but your calculator only works for log base 10 and log base 3 calculations if you're trying to just plug them in and solve, right? So right here, what you would do, it says, what is the value of the natural logarithm when x equals 3? All right, so that's saying ln of 3. All right, it's asking you to plug in ln of 3 in your calculator. Okay. Okay. And again, just a quick calculator check. I'll do one of these and let you try the others here. All right, but this is just saying plug in this value for x. So I literally hit in my calculator the ln button, and I typed in 0.1 for my x value. All right, and it got me a negative 2.30, you know, more decimal places than are shown here, but it's going to give me a negative 2.3. All right, and same thing here. You're going to check against all of these to make sure you understand what's going on with your calculator and see if you can also, of course, pick up some trends here. All right. But once you've done that and you can check against it yourself, again, please make sure you do this in your calculator, because I really don't like, or I really don't want you to mess up something like a calculator mistake here. All right, but we're going to get these values. All right, and if we were to input them graphically, all right, if we were to draw them out graphically, that's what they're wanting you to do here. So find, okay, 2.69. All right, and obviously I'm nowhere near that right now, so I'd have to go 2.6, too far, all right, about there. Oh, and my computer, of course, is on the fritz here, so apologies. Okay, but what it's trying to get you to do is plot those points graphically here to see what it would look like. All right, and then obviously, if you got to plot them, it would look something like this. All right, it would look something like this. All right, and when we connect the points, okay, it gives us our graph using this natural logarithmic function. So our ln of x would give us a graph that looks something like this. All right, and obviously they did a lot better job of matching up that 2, comma 0.69 than I did. All right, but it would give you a graph that looks something like this here. All right, and you can drag these along to check those points if you don't believe them, but they're usually pretty good about that. So that's what our graph is going to look like for one of our special logarithmic functions, that ln or log base e. All right. If we took a look at our log base b of x, all right, in general, all right, our logarithmic functions, okay, if we look at our logarithmic functions in general, okay, we can change the base value. So if I change my base value to a really large number, hopefully you notice it kind of flattened out here. It started to get a little bit closer to the x-axis, versus if I go really, really far, it starts to get larger here. All right, and as we talked about, if I go between 1 and 0, all right, if I go between 1 and 0, just like in our exponential, right, just like in our exponential graph, we have a change, right? We're going to have a change also in our inverse function here for logarithms. All right, and obviously, of course, we're going to talk more about that. But notice that when I go between 0 and 1, my graph changes from increasing to now decreasing. All right, so like I just mentioned to you, if b is greater than 1, the graph is increasing. If b is less than 1, the graph is decreasing. All right. And notice, okay, it says right here, note that the base can't be less than or equal to 0 for the same reason, right? So it won't even let us, because it's the same reasons as our exponential function can't be less than or equal to 0, right? We have issues with that negative inputs or outputs, depending on if we're looking at our exponential or logarithmic, all right? And then here, what happens when x is 0? Okay, again, that's saying what value will give us 0, and the answer is nothing, unfortunately. All right, so what happens when x is 0? We're going to have an asymptote there. We're going to have an asymptote there, right? Again, a horizontal asymptote is what we have for our exponential functions. All right, and so since we flipped it and we're looking at our inverse, okay, we're now going to, instead of having a horizontal asymptote, we will have a vertical asymptote. We will have a vertical asymptote. All right, we'll have a vertical asymptote, and I already told you that, but I'll go through it again. The vertical asymptote being at x equals 0. All right, being at x equals 0. Even if I pull this guy in, right, notice I'm never crossing this 0 axis, right? So in our exponential, it was the y direction, and obviously when we flip those, it now becomes our vertical asymptote. All right. Additionally here, right, since the y-axis is an asymptote, the graphs of our logarithmic function does not cross the y-axis. All right, therefore, we do not have a y-intercept, okay? Instead of having the same y-intercept, lo and behold, they're going to have the same x-intercept, all right? And that x-intercept is going to be at the point 1, 0, right? So think about it. It obviously makes sense here. We just flipped what we did with our exponential. Our exponential, we had a y-intercept at 0, 1. Now, since we flipped it and we're dealing with the inverse function, we have an x-intercept at 1, 0. All right, our x-intercept at 1, 0. Okay, our x-intercept at 1, 0. Obviously being right here where it's halfway between this value of 2. Maybe if there we go. Okay, you can see that we're still going to cross our x-axis at that point 1, 0. Okay, so then if we look at our domain and range here, okay, hopefully we're picking up some trends and realizing that we flipped across our x and our y axes. So what we had for our domain in our exponential is now going to be our range in our logarithmic, and our range in our exponential is now going to be the domain in the logarithmic. All right, so looking here, okay, so looking, oh gosh, every time. All right, so if we look here, okay, our domain, it's asking what can our x values be? Well, hopefully you notice that our x value has to be greater than 0. Kind of, we have a vertical asymptote at x equals 0, so our values have to be positive for our domain here. All right, but our range is now no longer restricted. Our range can be any value or all real values. So looking here, okay, knowing that those are our domain and ranges, okay, knowing that those are our domain and ranges, we can now do our translations of shifting. All right, so if we shift 3 units up here, okay, we still have our domain greater than 0 and our range is still all real numbers, right? And all we did was we plus 3. All right, and the same thing's going to happen if we go down 4. All right, we're going to have a minus 4. There's no change to our domain and range. All right, but when we deal with horizontal translations, again, we're moving to the left and to the right, okay? now when we're moving to the left and to the right, we have a change. Our domain is greater than whatever our shift is. So if you notice here, okay, our horizontal asymptote was originally at this x equals 0. So when we move 2 units to the right, so does our horizontal asymptote, right? So instead of now our domain being x is greater than 0, x just has to be greater than 2. Or if we moved our units to the left, right, we move 7 units to the left, so our x values have to be greater than x equals 7. Or sorry, x equals negative 7. All right. Again, that is a big change. All right. And then another change here is that since we have shifted, along the horizontal axes or along our x-axis, we have now changed our x-intercept. Right? So we've changed it by the value that we have added or subtracted, right? So when we moved 2 units to the right, okay, instead of again it being at 1, 0, now we add it, okay, and we're now at 3, 0, because we moved to the right. All right, same thing when we moved to the left. All right, we moved 7 units to the left, so instead of being at 1, 0, we had to do 1 minus 7, which gives us this negative 6 value. Okay. Obviously, the next progression here is stretches and compression. So vertically, all right, if we multiply by a number greater than 1, we're going to stretch. And if we have a number less than 1, we'll have a compression here. All right, and similarly here, if we multiply it by a negative number, it also flips it across our x-axis. All right, so if we vertically stretch by 4 units, all right, we vertically stretch by 4 units, we just multiply by 4 on the outside. All right, and if we compress by half of a unit, right, we're going to multiply it by half. All right, and with these guys here, there's no change to our intercepts, right, and we still have the same domain and range values here. Okay, horizontally, of course, again, stretching is still greater than 1. Compression is between 0 and 1, and if we have a negative value, it flips, but when we're dealing with horizontal stretches, it now flips it across the y-axis. All right, so again, if we stretch by a fourth of a unit here, all right, we will have it being multiplied by the inside, right, and our compression, of course, being multiplying the inside by that 7. All right, and that's gonna be the trick there. All right, since there's no negative values, there's no flipping across our y-axes. All right, now of course combining is gonna be the trick here, and I just want to focus on one of these for the sake of time. I want to shift 4 units up, horizontally compress by 2 units, and then flip across the y-axis. So what that's gonna look like, shifting 4 units up, so plus 4. Horizontally compress by the unit of 2, and we flip across the y-axis. All right, so since we're going to horizontally compress and flip across the y-axis here, we just multiply our inside value by a negative 2. Right? We multiply our x value by a negative 2. All right, so again, breaking it really down step by step here. All right, what do you notice about the function? All right, first question, is it a reflection? Is it a reflection? The answer is, of course, yes it is, right? Yes, of course it is, because it's got a negative 3 value out here. So it's got a negative 3 value. So that makes it a reflection across our x-axis because of this negative 3 value here. All right. Next question, was it translated? And if so, how? Well, we've got a minus 4 outside of our x value. So that means, yes, it was translated, and it was translated down. And then finally, compression or stretch. And yes, it was. I've got a 3 value outside of my x, so therefore it was vertically stretched. It was vertically stretched. All right, so again, those are the 3 questions: reflection, translation, stretch, or compression. All right, and again, you can take some time to dissect what this individually means here, but obviously we shifted down, okay, we stretched and we flipped, and then adding it both together will look like this function here. All right. So the graph of a logarithmic function increases or decreases depending on the base value, right? Depending on the base value, just like normal here. All right. And understanding the characteristics is, of course, going to be really beneficial for us, right? That's always the key. All right. So again, answering those three questions. Is there a translation? Is there a reflection? And is there a stretch or compression? Right? Those are going to be the questions that will help you. And then obviously knowing the base characteristics or the characteristics for our base functions will help you with the domain, the intercepts, asymptotes, all of that kind of information here. All right. So I'll let you, of course, try those on your own. Same thing here, all right, really taking some time to look at the graphs, all right, really taking some time to look at the graphs. And of course, it's going to be the key point, where is the x-intercept for this graph here, right? And obviously it's at this -2 value, right? So obviously we now know that there was a translation, okay? So pointing out the direction the graph, is it increasing or decreasing, all right? And then where does it cross the x-axis? That will tell you a lot of information. Okay, that will tell you a lot of information with graphs here. All right. So, of course, then knowing the characteristics is going to be key. I can't stress that enough. Knowing the characteristics, or having that sheet handy and understanding how to utilize it. All right. But looking here, it's asking you, what's the domain for the logarithmic function? So what are the x values that this function can be? Again, absolute worst case scenario, you can always just plug this function into your graphing calculator. Plug in log base 10 of x and see what happens, right? We can do that because it's got this base 10 here, right? It's got base 10. If it's base 10 or base e, which is our ln function, you can immediately plug it into your graphing calculator. If it's a base 2 or a base 4, right, that's not as easy for you to plug into your graphing calculator. So you're going to have to know those characteristics. Oh my gosh, it's like I read this before, right? Base 2 here, you can't just plug that in, right? You've got to understand the characteristics that function will have. All right, same thing with this base 0.5. All right, these are really good check questions for you before you go and take your quiz here. All right, so of course now we're going to end with a real world problem, okay? And we're dealing with earthquakes. All right, we're dealing with earthquakes. So again, we can look at this equation here, which relates the energy of an earthquake to its magnitude on the thing called the Richter scale. All right, and it's saying Rx is the magnitude of the earthquake, X is the energy of the earthquake in this thing called kilowatt hours. All right, that's just a unit of measurement. All right, an earthquake that measures 2 on the Richter scale has about 1.7 kilowatts hour of energy. How much more energy does an earthquake have as if it measures 3 on the Richter scale? Okay, so in order to solve this, we're going to have to find the kilowatts of hour that measures a 3 on the Richter scale. Okay, well, and we know that obviously based on the last question here. All right, based on the last question. All right, and what that's going to do is since it's asking how much more, what we're going to have to do is we're going to have to solve for the energy. All right, we're going to have to solve for the energy, then we're going to have to do a subtraction. Right, we're going to have to do a subtraction. Oh, you want to solve for x in this problem because it's saying how much more energy, x is the energy. All right, so that's how we dissect that problem there. Okay, so then what we could do is we can solve this by evaluating using our graphing tool here. All right, and what we could do is plug in values, right? Plug in values, and this guy here. Sorry. Plug in values here, and this guy would give us outputs. All right, it'll fill in this graph for us. Right, it'll fill in this graph for us, and that's what they were saying, making sure that you change your x values, or make sure you change your window so that you can see, you can actually see what's going on here graphically. Because again, if I get too close or too far away, it's hard to figure out a difference. And what this is asking us to do is obviously we're trying to figure out where the output here is a 2 or a 3 on the Richter scale, right? We're trying to figure out where it's going to be a 3 on the Richter scale, because X here, like we said earlier, is our energy input. So we could just keep filling in values. So it's more than 500, but it's less than 1,000, as we found out here to get a 3 on our Richter scale. So maybe it's 750. Nope. Still less than 750. 600. Getting closer. 575, right? Somewhere, and you can keep going and going and going until you figure out the value of X that will make Y equal to 3, right? So that's one way of approaching this. All right. And what we could find out then, of course, is the energy when it's equal to 3. So clearly here, our red dot, if I move it and I'm really careful, our red dot equals 3. Our energy is 534.03. All right, so that's what we need in terms of our energy. So at X equals 534.03, we're going to have a Richter scale reading of 3 here. All right, we're going to have a Richter scale reading of 3. So then we would have our value. We could do our subtraction to figure out how much more energy. It would just be 534.03 minus this 17.3 here. All right, so we could do that easily. All right, so that would be how we could solve that problem. Looking at our study guide to finish this up here. All right, understanding graphically, right? Understanding graphically is specifically the base 10 and our base E or our natural log, okay? Understanding those values here, all right? And first, looking at just calculators, okay? Looking at just calculators. You can only use your calculator to solve ln or log base 10 based problems, okay? Those are the only two. All right, the other thing I want to point out here is they're very specific about rounding to 2 decimal places. So when you write your answers for your quizzes and your tests, make sure you keep this in mind. They are specifically looking for 2 decimal places if there are decimals. If it's a whole number, obviously just write the whole number. Or pay attention to specific directions. But in general, if you need to round it to 2 decimal places. All right, and then obviously, of course, understanding if the base is greater than 1, we talked about it being increasing, versus if it's between 0 and 1, we have decreasing. And again, we never have a base that is a negative value. All right. What happens with the shape? Where's our intercept? Again, we're now not dealing with y-intercepts. We're dealing with x-intercepts, and it's going to be at 1, 0, right? We're going to have a vertical asymptote at x equals 0 or on our y-axis. And then our domain and range are adjusted accordingly, right? So our domain has to be x is greater than 0 or positive, and our range is all real numbers. All right. So then looking at number 4, this is talking about our earthquake problem. All right, so the steps for solving that was graph the function and basically find the point where we get y equal to 3. All right, once we have done that, we can then subtract the difference between them. All right, and when we did that, we ended up with 520 more units of energy when we go from a Richter scale reading of 2 to 3. All right, then finally here for our checkup. Okay, finally here for our checkup. So looking at this here, all right, it's going to be a lot of questions asking you about the characteristics of the different graphs here. So finding the domain and range with our different graphs. Is there changes? Is there not? All right, what happens to the x-intercept? Is the function increasing or decreasing, right? So again, just being able to look at equations and identify some basic characteristics here. That's going to be the key. All right, and then obviously this unit here is finished off, or sorry, this lesson here is finished off with a quiz. All right, so you've got 3 quizzes, 1 extra credit opportunity, hopefully not too much work for you. So try to get those finished up as quickly as possible. Tomorrow we'll pick this up. We'll cover 3.7 to 3.9, and we'll end there for tomorrow. Okay, so sorry, 3.7 to 3.9. All right, if you got any questions, please feel free to reach out. Other than that, have a great, lovely night. I'll see you guys tomorrow morning.